A better way to understand the problem in the previous video is to consider a general case for the perimeter. So rather than looking at a specific number for the perimeter, consider it for a general case where the perimeter is just p. So when the perimeter is p, this here perimeter equals this, and then so similar to the previous video, we still need to set up an equation for the volume here. So we need pi r squared here, and then times this distance here. So similar to the previous video, but this time it's for the perimeter of p rather than 20. Okay, so looking at this, and then so similar to the previous video, the volume is given by this. Okay, so this is what we have so far. So far this is what we've got. We've got the perimeter here, and the volume is given by this. So now use implicit differentiation, but bear in mind that we are varying x here. We are sliding x back and forth here. Okay, and then when you slide x back and forth, y reacts accordingly. Okay, so because of this constraint here, y will react. So as you slide x back and forth, y will react accordingly, meaning y is a function of x. Okay, and now if you slide x back and forth here, we are varying x. Now as you vary x, you actually vary the volume. The volume here will change accordingly. So volume is a function of x. Okay, now as you slide x back and forth here, the perimeter will always be the same. The perimeter will always be the same. It's the perimeter is always the same. So the perimeter is not really a function of x. So this here is a function of x. This here is a function of x. The perimeter here is a constant. So when you come to differentiate it, well, just bear in mind that this here is a constant, and this one here, when you differentiate it, you're going to need dy by dx. You're going to need to stick dy by dx in here and here. So currently we are here and here. So now use implicit differentiation here. So this will then become this. Okay. So if you differentiate this, so when you differentiate this, p is a constant, so that will become 0. We'll differentiate this with respect to x. Okay, because we are sliding x back and forth, we are varying x, so we are differentiating this with respect to x. So differentiate this, it will be 0. Differentiate this, it will be, well, with respect to x, that will be 2. Now differentiate this with respect to x, so that will be 2. And then because y is a function of x, it's like a chain rule here. So you're going to need dy by dx. Okay, so differentiating this will give you this, which is this here. Okay, rearrange it. So rearrange it to make dy by dx a subject. So that would be -1. Okay, and then now we need to hang on. Sorry. So we've done dy by dx now. Now going back to here. So we've done this. Now we need to implicitly differentiate this. Okay. So remember that v here is a function of x. So when you differentiate it, it will become dv by dx. Okay. And then here hang on. We are now going to try and use implicit differentiation on this one here. So looking at this here, visualize this as, visualize that as this. Okay, so you've got one block multiplying another block. Okay, hang on. Let me scroll back so that you can see. Hang on. So now we are trying to implicitly differentiate this. So now visualize this here as this. So you've got one thing here. So it's like one thing multiplying another thing. So visualize this thing here as this. Okay, so you've got one thing multiplying another thing. So bear in mind that we are differentiating with respect to x. So because y is a function of x here, we've got to use a product rule here. So hang on. Differentiate this. This will give you dy. Remember, we are differentiating the whole thing here with respect to x. So this will become this. And then here you've got to use the product rule. So differentiate this, leave this the same. So differentiating this will give you this, and leave this the same. That will then give you this. Okay. The second part of the product rule is leave this the same, and then differentiate this, giving you this. Okay. And then earlier, hang on, and then that will then take you to here, because dy by dx earlier we worked out that it's minus 1. So dy by dx here earlier it was minus 1. Okay, so this thing here will become minus 1. So basically this minus 1 times this will become a minus that. So basically it will become this. Okay, so now we need to set the gradient to be 0. Okay, so now come to this stage. Come this stage here. What you've done when you get to this stage here, what you've done here is that you've buried the constraint into this stage here. So you've buried the perimeter being fixed into this thing here, and then you've also buried, if that makes sense, buried the gradient to be 0 into this thing here, if that makes sense. Well, basically, when you get to this stage here, you've taken into account the perimeter being fixed, and you've taken into account that the gradient has to be 0 because you set it to be 0. So when you get to this stage here, you've taken care of the perimeter, and you've taken care of the gradient being 0. Okay, so when you get to this stage here, you've taken care of pretty much everything. So now you've got one block minusing another block. So add this block to both sides. That will then give you this, and then blah blah blah. Times both sides by 2 pi. That will then give you this, and then divide both sides by x. That will then give you this. Okay, so when you get to this stage here, what it means is that make x twice the length of y in order to maximize the volume here. Okay, so basically when you get to this stage here, you should be able to deduce that this length here must be twice the length of this. Okay.